In this lecture, we'll finish up the first chapter of our ECE 301 workbook. This is on power calculation resistances, and then we'll go ahead and begin chapter 2 on our fundamental approaches to doing circuit analysis. So I've written here notes from the bottom of page 18 here on the top of 19, just so I don't have to flip pages so quickly. But just as a review, remember power is simply the product of your voltage and your current. And if the voltage and the current are in passive reference configuration, PRC, then the energy is being absorbed by the circuit element. Similarly, if you have a negative sign for power, in other words, negative watts, then your energy is being supplied by the circuit element to other parts of the circuit. Using Ohm's law for voltage, you can quickly see another potential formula that you could use for power would be this form. If you have a resistance, and you could use resistance times the square of the current. So that's just using the fact that we know that V equals IR, okay? If you solve for Ohm's law for the current, you could also write another form of power as power is the voltage squared divided by R. So this allows us a couple of opportunities to get your power given a resistance with one of the two components, either voltage or current, right? So even though the power formula says, hey, it's voltage times current, if you're dealing with resistances, you can get the power for that circuit element by using the current or the voltage for that resistance, okay? So power for a resistance is positive, regardless for the sign of voltage or current. That's very important because with resistances, we are always absorbing energy. Let me say that again. With resistances, you are always absorbing energy. You're not delivering. These are the components, for example, for heating coils, all right? You're trying to absorb the heat to get hotter and hotter, not, to dissipate, all right? Space heater is typically, for example, coiled nichrome wire. It becomes red hot, and you've seen examples of that. And that's delivering heat to the surrounding area because it's absorbing the energy, right? Keep in mind that a resistance is commonly used to model devices in which electrical power is converted into forms other than heat. For example, a loudspeaker amplifiers may have a resistance of, say, 8 ohms, and a transmitting antenna may have a resistance of 50 ohms, all right? So this is the idea of power being converted into other energy forms, not just heat. A resistor, of course, is a two-terminal device composed of conductive materials. Its resistance is a circuit property in which voltage is always proportional to the current, and that proportionality constant we usually refer to as capital R with the resistance. But we're going to do a couple of examples of power computations here, all right? And we're just going to use some of our formulas that we've talked about above to see how they can apply. So the first example is example 13. Suppose you have an electrical heater, and the rating for that heater is 1500 watts, all right? And it's operated with 120, when operated from 120 volts, which is the case here in the United States. So the task is, let's find the resistance of the heater element that is obviously getting warmer and warmer, and its operating current. So first thing to realize is, what do we know? We know the power and we know the voltage. So knowing that, we have this relation that power is just the square of the voltage divided by the resistance, okay? So this should get us the resistance of that heater element, right? We just have to plug it in. Or if you want to resolve this for the resistance, right? Flip it over, multiply, you would get the resistance is just the, it's the voltage squared, right? Divided by the power, okay? Just solving that for resistance, right? Then we can plug in values. We have 120 volts, which will be squared, and we are dividing by 1500 watts. Okay, I'm not putting the units in there because we know we should be getting ohms back. And if you take the calculator out, and of course for any of these problems, whether it be in the homework or in the quizzes, you have a calculator available, you can use it, of course. 120 squared divided by 1500, I've already done the calculation, that's 9.6 ohms, right? Okay, right? And maybe just to double check the units, what we had here was volts squared over resistance, which is another way of looking at resistance, is volts times amperes, correct? And dividing through it, canceling on an extra volts would be volt per amperes, and that of course is an ohm, okay? So it's just a good idea that, you know, sometimes when you're doing this analysis, if you want to put the units in with the numerical values, that's fine, okay? But we know that we are going to get ohms out of this, okay? All right. We were also asked to find the operating current, okay? So we would go to Ohm's law then. And of course, Ohm's law tells us that the voltage is the product of the current times the proportionality constant R, or you could just say that, well, the current we're looking for is nothing but the voltage divided by the resistance, R, and then we'll just plug our values in. In this case, I'll put the units in. That's 120 volts, right? Divided by the resistance, which is 9.6 ohms. Another way of thinking of ohms, of course, is volts per ampere, okay? And then you can see after calculating the value that you're going to get out of that, 120 divided by 9.6 turns out to be about 12.5. And you can see the volts cancel out. You have 1 over amps. So that's just amps, okay? Right? So we know that the operating current is 12.5 amps. And we know that the resistance of the heater element is about just almost 10, but about 9.6 ohms, okay? Right. So keep in mind, just as a review, the resistance, because we'll use this in a second, also resistance can be physically determined by the resistivity constant for the material used to make it, the connector that's used to make it, times the length of it divided by the cross-sectional, excuse me, not the cross-section, just by the area in terms of the wire that's been used, okay, of the cross-section, I guess I should say, okay. And of course, if you multiply through this, you could show that, well, if we cross a multiply, rho times L is equal to resistance times the area, and we could then get the length must be the resistance times the area divided by the resistivity. And the reason why I wanted to do that is in the next segment here. It says that if for the same electrical heater, all right, if the resistance we determined above is in the form of a nichrome wire, so now we actually have some material properties, and let's suppose it was a nichrome wire, right, and it had a diameter of 1.6 millimeters, what must be the length of the wire to achieve that 9.6 ohms with that operating current of 12.5 amps to ultimately achieve 1500 watts. So you see all of these values and all of these measures work together in tandem to achieve that power, all right? So using what we just derived for the length, using our physical design of a resistance, then we know that we can plug in some values here. So again, L is just the resistance, which we know what it is, 9.6 ohms again, times the area divided by rho, okay? So in this case, we'll plug in some values, 9.6 ohms, and we need the cross-sectional area, okay? All right, so we have to think about how do we get the cross-sectional area. So let's just come over here to the side. Remember our formula, if it was given if the wire is given in terms of diameter, which in this case it is, pi diameter squared over 4, remember? Yes, we know that the standard form is area is pi r squared, but if you're given the diameter, remember the diameter is twice the radius, and so we're just specifying it this way. And in fact, we know what the diameter is given as. Here it is, 1.6 millimeters. I hope you were going to say, yes, you need to convert that. Convert it to meters. Always convert that to meters. So it's 1.6 times 10 to the minus 3, because we said it was millimeters, squared, okay? So again, watch your units, always convert to meters, okay? Finishing that calculation out, you need to divide this whole thing by 4. And if you do that, and I've already done that with a calculator, you should get 2.01 times 10 to the minus 6 meters squared, correct? Because that would be meters inside there, you're squaring the meters. And of course, from exponent wise, you can see what's gonna happen, 10 to the minus 3 times 2, you should be getting something order of 10 to the minus 6 back. So we now know what the area is for that wire. So we'll plug that in, 2.01 times 10 to the minus 6 meters squared. And that needs to be divided by the resistivity. And the resistivity is given by this value, rho. So that would be 1.12 times 10 to the minus 6. And if you don't remember, I'll just remind you here, the units of resistivity should be ohm meters, okay? So this will be given always in ohm meters. Close our parentheses, and let's maybe simplify this computation because we can see what's going to happen here. You can see that these 10 to the minus 6 terms are going to go out very nicely. So you're going to have 9.6 times 2.01, and that is going to be divided by 1.12. The 10 to the minus 6 term has removed itself. Meters goes into meters squared, leaving meters. That's exactly what we need to get back. So make sure our units are lining up correctly. Absolutely, we're getting meters back. That's what we should. And this should turn out to be about 19.3 in the numerator divided by the 1.12, again, in meters. And it turns out the wire is about 17.2 meters, okay? That's a fairly significant coil. If you think about the length, meter a little bit, about a yard. So it's almost, it's the neighborhood of 17 yards of wire there. So it's pretty significant for that heater unit, okay? So that was one example of doing power computations. Again, this case using what we were given, determining the current given Ohm's law for the voltage and resistance, and then a little bit of details about the physical properties of the resistance giving resistivity. The last example before we move into chapter 2 suggests that we look at an incandescent electric light bulb with a little bit lower power rating. This time it's about 100 watts, which is reasonable. Maybe a little bit brighter than you typically would put in a lamp, but depends on your needs, I suppose. But 100 watts, and again, we are using voltage of 120. And the goal is to determine the resistance at its operating temperature and operating current, okay? So again, we are given voltage in watts. So a good formula to start with for power is what? V squared over R. So it's just another example that you don't have to go to voltage times current, okay? In this case, we can, again, solve for the resistance like we did above. That is, again, just voltage squared over power because we were given a power rating. So we know this is 120 volts. I'll go ahead and put the unit in squared, divided by the power rating in watts, which was 100 watts, okay? And again, realizing that we can represent, the watts in terms of rates related to voltage in amperes, we should be able to get back out of this ohms, and the value should be 144 ohms, okay? Right. So that would be a very significantly larger resistance, okay, for this particular light bulb compared to that electric heating unit, okay? Much, much higher resistance, all right? And if we wanted to get, oh, and let's do a unit check again. It might be helpful just to make sure recall that watts are volts times amperes. And so if you're doing volts squared divided by volts times amperes, you can see clearly what you're going to end up with is volts over amps, and that is another name for ohms, okay? So again, sometimes when you're using units and you're just not sure, you can always go back to the definition and say, yes, I need to be getting ohms back. So it's just a double check on our units there, right? You're also asked to get the operating current. Again, we'll use Ohm's law. And with Ohm's law, we know that, again, you can start with the fundamental definition and then solve what you need. We're asked for current. So current is the ratio of voltage to resistance, okay? And in this case, you would have 120 volts divided by this 144 ohms, but remember another name for that is volts per amperes, so that the volt units cancel out and you have 1 over amp, which is an amp, and doing the math, it's less than 1, so it's 0.83 and it repeats amperes. So notice for the light bulb, much less current. So it's kind of interesting just to see the scale difference between the currents needed to get this very high power versus very simple light bulb doesn't need much current at all, okay? Of course, this is more dangerous in terms of potential harm to yourself than this. But anyway, it's kind of nice to see those differences. And let's do one more example, pushing up resistance even higher, okay? And this is an example in a TV receiver. Suppose we have 1K, so that's 1,000 ohm resistance used in a TV receiver, and the power rating is very low, a quarter of a watt, 0.25 watt. And we want to determine the current and the voltage, just so that we can see, again, relative scale of differences of how voltages and current, what typical values you get with these kinds of resistance values and power, okay? Very high resistance, very low power. So we'll flip over to the top of page 20 for this last box in this chapter. And just to do the calculation, just remember we're doing this component in the TV receiver, and the resistance is 1K ohms. And just so we understand, when we say 1K, we're talking about 10 to the third. This is plus 3. I'm just sort of illustrating. Many times we're doing units and we're using negative exponents. So this is a big one. So we're doing 10 to the third, all right? And it told us that the maximum power that we can generate with this is 0.25 watts, okay? Right? So using our formula relation for power and voltage, then the maximum voltage that's possible squared would be equal to the product of that maximum power times the resistance, okay? I'm just using the subscript max just because that's how the power rating was given to us, okay? And so the corresponding voltage, it makes sense to say, well, then it's the maximum voltage possible. And again, we've given the values here, 0.25 for the watts being multiplied by the resistance value, which is now 10 to the third. It will call shifting of the decimal there 3 times, so you'll get 250 for the square. We just have to be careful, and this is typical sometimes. If you're looking at voltage this way, you got to be careful that's the square. So that means the maximum voltage is the square root of 250, which is about 15.8 volts, okay? Right? So we're talking about 15.8 volt, a little bit less than 16 volts, right? Versus looking at 120 volts was we were using for the other 2 components a minute ago. So this is very low voltage, okay? And if you needed the current or were interested in the current here, then again, via Ohm's law, one more time, we know from Ohm's law, voltage equals current times resistance, or in this case, it's the maximum voltage divided by the resistance, okay? Again, because this particular voltage is for the maximum power rating, okay? Just using consistent subscripts. And we already know what Vmax is. That's 15.8 volts. And we are dividing by 10 to the third ohms, which is again volts per amperes. And we will get amperes back, which is excellent. But we're going to get a really small value now. So now the current is even much, much less. In fact, it's 0.0158 amps. And if we just shifted that decimal 3 times, right? Yes, we'll shift it 1, 2, 3 times. This will be equivalent to 15.8 milliamps. So just to illustrate, we are now on a completely different scale of current for such a very low power component. Okay. So those are just useful ways of getting to the power. This will come back later when we need to get power ratings for different circuit elements, and maybe we just have current or maybe we just have voltage, but we don't need to have both, okay? We can get it with both, but if we don't, it's no problem. As long as I have my resistance, I can get the power for those circuit elements of the resistance. Okay, so that finishes chapter 1, and we're just going to start briefly in chapter 2 to do a few problems. I won't do that many just for the sake of time of this video, but I want to get started with it, and then we'll pick up on the next lecture. We're doing a couple of more, all right? So the goal here is basically to find the unknowns we're interested in, okay? Using what we have studied so far with all the properties of the resistances and the properties of current, voltage, and power, okay? So let's assume the reference polarities agree with this very simple circuit design here and the current directions as well. So what we're going to do is notice a couple of things here before we get started. This is a closed path, so there is a current flowing through. So let's represent a current flowing through, and we'll call it I sub R, indicating that it is flowing through this resistance, but it's a closed loop. So there is only these 2 components here, all right, are attached end to end. So there's only, if we think of looking at, one current flowing through, and we have one current flowing through the resistance here, we also have a current flowing through the voltage source here. So I'll indicate it as I sub S just for source, right? Now, I call myself for a second, well, these are not in series. They are connected end to end. They are in parallel, okay? All right? So even though I'm going to represent the voltage here, voltage R, plus and minus, notice that because they're in parallel, I'm going to make their voltages, the polarities agree. In other words, it's typically a good convention to do that. If these 2 components are in parallel, if that's the top node is the positive, then I'll make the top node positive on the resistance as well, all right? So one way of saying that is maybe we'll make this convention that in parallel, so align voltage polarities. So just, it's a good practice to just do that in general when you have them in parallel. It doesn't always have to be the case. You have to have you must have a required direction. For the current through a resistance. And this is not arbitrary here because it has to absorb energy. That's the whole point of the resistance. You've got to make sure it's in, whoops, almost missed it, PRC. You've got to make sure you're in PRC. That means the current must flow into the positive pole, okay, of the voltage associated with that resistance. So let me say that again. When you're assigning the reference direction for the current flowing into a resistance, make sure it's flowing into the positive pole of voltage for that resistance, okay? Energy has to be absorbed. Power must be positive, okay? Very important, right? Now, you may notice carefully here that for the voltage source, I did not make that PRC. Well, what does that mean? Well, that means energy is going to be delivered, right, by the voltage source. So this is that law of conservation playing out for us, that on one side of the circuit, you are delivering the energy. On the other side of the circuit, in this case, it's only two elements, you are absorbing it. So it needs to be consistent from that physical sense there, so that these directions are not just totally arbitrary. Of course, you have nodes here for KCL. These are two possible nodes here that you could use. So we could say possible nodes for KCL. Okay. So we just have a sort of understanding of how we can apply some of the tech laws that the Kirchhoff laws, I should be careful I say that, in the circuit. So making sure that we're looking at nodes in which, again, conductors, there's no circuit elements between these two connection points up there, right? So those are possible nodes for KCL. So for this particular circuit, suppose that the voltage source is 10 volts. So this turns out we're going to make an assumption here that this is equal to 10 volts. And we're going to assume the resistance is 5 ohms, okay? So the goal of this first task is to determine the current and the voltage for each circuit element, right? So in this case, there are only two. You have current and voltages for a voltage source and a resistance. There are only two elements, okay? So we just need to go through that and determine the voltages and determine the currents. We have a closed path here. So when you have a closed path, KVL is possible. So let's do KVL. And it's always a good idea to indicate the direction just in case we're debugging or we're looking at someone else's work. So for this particular simple circuit, we're going to go KVL clockwise. And if we go clockwise, we are not PRC here. We are coming into the negative component, voltage component for the source, but we are PRC in the other one. That's plus VR, and that must be equal to 0. Okay. So in this case, that tells us something here, all right? So we know that the voltage source is minus 10. Another way of saying this is that whatever the voltage source is, that's the same voltage as the resistance voltage, is the same as the voltage source. That's actually not too difficult to follow, right? Because they are in parallel. So we know magnitude-wise, they should be the same, all right? So in this case, we know that VR is 10 volts, okay? And we don't need to change the polarities, right? Because the fact that the current flows into the different poles is taken account for us, the fact that the energy will be absorbed by one and delivered by the other. If we were to flip those polarities, say, then things are going to get a little bit more complicated because then some current's going to have to be negative, right? All right, so via Ohm's law, since we're talking about currents, if we look at Ohm's law, right, we know that the current through that resistance must be the ratio of the voltage to the resistance R, right? Again, that's another way of looking at Ohm's law. And in this case, it's 10 volts divided by the 5 ohms, and that's just going to be 2 amps. So we know that there are 2 amps flowing through that 5 ohm resistance, okay? And getting a relationship between the currents, that's usually KCL. And we could do, any of those nodes would be fine to look at it from the perspective. We'll just say the top node. Again, it's a good idea to make a habit of specifying what node you're looking at. So we're looking at this top node here, okay? And what we do know is if we were to write this in terms of incoming, leaving, outgoing currents, you have an outgoing IR and you have an incoming IS. So clearly those two currents have to be the same and they're both 2 amps, okay? But another interesting thing here has happened is notice that the voltages were the same, but the currents were same as well, because this very simple example loop illustrates that yes, they're connected end to end, but they're also in series. So here's one very simple example, doesn't typically happen, where because you only have 2 elements, they're both in series and in parallel at the same time. So if they're both in series, then there can only be one current flowing. In fact, it's 2 amps. Okay, let me say it again. We know the parallel units should be sharing voltage, and we know that elements in series share current. This very simple example has both of those scenarios. So that's why the voltages turn out to be the same and the currents turn out to be the same. Okay. All right. Finally, let's finish out with power. Calculating the power for each of the elements in the circuit. Very simple example, of course. And let's, in this case, we have all the information we need. I'm flipping over to the back of the page here of 22, but we can write power equations this way. You could say, well, if I know what the voltage is for my resistance and the current for my resistance, multiplying those two together, I can get power, okay? And another thing to realize, of course, is that the resistance was in PRC. That was important. So that is the correct formula to use. So make sure, ask yourself when you do these calculations for power or Ohm's law, are we in passive reference? In this case, yes, because the current flows into the positive voltage pole. So we just plug in your values that we just obtained. It's always 10 times 2, and you would get a positive 20 watts. That makes sense because that's going to be the energy absorbed by that resistance, okay? Just so that we could have gotten it another way you could have gotten the power, right? Could have been squaring the current times the resistance, just showing you could do it another way. In this case, it would have been what? 2 was the amps squared times the 5 ohm resistance. That would get you positive 20 watts, okay? So same answer either way. We'll just say energy is absorbed regardless, okay? Either way. And then finally, if we do the power for the source, the voltage source, okay? Now, just quickly, just flip back over just for a second. Ask yourself, is it in PRC? The representation of the current direction looks like it comes in the negative initially, not the positive. So we need to insert the negative sign because that is a representation of not PRC. Its voltage times its current. Well, it's the same values again. It's minus 10 times 2, and we get minus 20 watts. So I know the values here are very trivial, but they're illustrating something very important in terms of consistency. That when you're looking at circuit analysis, if you compute all the powers associated with your circuit elements, energy must be conserved. So 20 watts is being supplied by that voltage source. Therefore, 20 watts needs to be absorbed, okay, by the resistance, right? So we're going to stop this lecture right here. It gave us a good example of the most simplest design. And we'll go through a couple other examples similar to this in the next lecture before we move on to taking advantage of series and parallel. So we're just basically using our power computations with Ohm's law to find voltages, currents, and power. See you next time.